Hi, my name is Renato, and I'll be presenting our paper, Learning Probabilistic Sentential Decision Diagrams by Sampling, which was submitted to the Knowledge Discovery, Mining, and Learning Symposium in 2020. This is joint work together with Denis Bauer from the University of São Paulo and Alessandro Antonucci from the KDMILE Institute for Artificial Intelligence. I'm going to give a short background first. So probabilistic sentential decision diagrams were introduced by Kisa et al. In 2014, and they're able to not only encode a logical constraint, but also learn from data. The structure of a probabilistic sentential decision diagram, also called a PSDD, is basically computational units, which are either OR gates, which correspond to a weighted summation over its children, or AND gates, and AND gates are products of their children. In particular, AND gates can have only two children. So leaves can either be literals, propositional literals, or a bottom, a constant bottom, or a Bernoulli distribution over a single variable. And not only that, but it also has to obey a certain V tree, a variable tree, which is here on the right-hand side, top right-hand side, which in this case encodes the variable ordering BADC. And the structure of the circuit has to obey this V tree. What I mean by that is the left child of a AND gate must have the variables in the left-hand side of the V tree. The left-hand side of the left child of a AND gate is also called a prime, and the right child is called the sub. And so, for instance, here we can see that the PSDD obeys the V tree, since on the left-hand side we have the conjunction A and B, which is on the left-hand side of the V tree, and on the right-hand side we have D or not D, which is inside the scope of the right-hand side of the V tree. And so this AND gate, together with its children, is called an element. A partition is a disjunction node together with its children element. And so I'm going to go through the existing structure learners that we have so far for probabilistic sentential decision diagrams. So the first paper on structure learning for PSDDs was by Liang et al. In 2017. And basically the idea was to learn a V tree through mutual information, and then pick an initial circuit, and then learn a new PSDD as an expansion of the initial circuit. This was done by recursively applying some small change, and then evaluating the score, and then greedily accepting the changes if the score is higher. And so what are these small changes that they did? Basically split. Split was done by taking an element and splitting into the positive literal and the negative literal, and this does not change the knowledge base. This does not change the logic constraints, because we're basically just conditioning on the positive and the negative. And another small change was clone. Clone basically took a disjunction node and cloned it into another disjunction node with the same constraints, so it did not change the knowledge base, and connect all of its children to the original disjunction node's children. Another structure learner that we have is Strudel by Deng et al. And basically their idea was, given a child tree, to learn a PSDD and its V tree. They did this by first learning a CLT, then extracting a V tree from the CLT, compiling it into a circuit, and then growing a circuit by applying that split operation that I mentioned earlier. And so, for instance, we have here on the left-hand side a CLT, and by taking this CLT, they managed to get a V tree on the middle here, and then from that V tree and from the CLT, they managed to construct a PSDD by recursing over the nodes and adding AND and OR gates. Now I'm going to go through our approach, which is learning by sampling, which we call a Monte Carlo structure learner. In this structure learning procedure, we do something different than the previous attempts, since in earlier work, they either grew or compiled existing models. And instead of this approach, we build a circuit solely from knowledge. So in our approach, we start off with a logic formula, so for instance, phi here, and we recursively decompose phi top-down through subsequent partitions. So we basically randomly sample a V tree by considering the problem of V tree as equivalent to the one of sampling open and closed parentheses. When we have a V tree and a formula, we can then decompose the formula into elements. What I mean by that is that we want a disjunction node over the elements, and the element should, the disjunction over the element should encode the original formula. And we do this by ensuring that the primes are exhaustive and mutually exclusive. You can also notice that since the circuit has to obey the V tree, then we know that the primes must have the variables that are mentioned in their circuit, the same variables that are mentioned in the V tree on the left-hand side. And so, for instance, here we have variables C, A, and B, and these C, A, and B should appear at least as a subset of them in their primes. And on the right-hand side, on the sub, they should appear a subset of them as D and E. And so when we figure this out, then we know that we can randomly sample an ordering. So for instance, B, C, and A of the scope of the V tree, left-hand side of the V tree. And then we can return a set of primes by naively expanding each possible prime through a recursive procedure. So for instance, here we expand B and not B, and then we expand B and C, and B and not C, and then we do this for every possible branch, and then we come up with an exponential number of primes, which are mutually exclusive and exhaustive. So unfortunately, this is exponential, and so it's not realistic. And so we want to find something smarter. And we can do this by forgetting a variable when it does not matter. So this means that we can basically marginalize a variable when the formula condition on positive literal is the same as the formula condition on the negative literal. So for instance, here we have B and not B, and we could have marginalized here on the top range, we could have marginalized C if C does not matter in the formula. And on the bottom side here, we have that C does matter in the formula, and so we must expand. And so we get these primes here, which are in fact mutually exclusive and exhaustive, but we also avoid computing an exponential number of primes by marginalizing. So in other words, we are given a random prime ordering of variables with respect to a V tree and a formula phi, and we generate a set of primes. We can get the subs by figuring out that the formula condition on the primes is exactly the subs. There is a special case, though, when the formula is a tautology, or if the variables in the random ordering are never mentioned in the formula. So for instance, if we have that the formula only mentions D and E, and the primes must be A, B, and C, for instance, then these variables are never mentioned in the formula, and thus they do not matter. And so when we have this case, then we have even more freedom, because we can stochastically marginalize with some probability P, for instance, any variable that we might want. So this is true because any operation on phi and the variable in the ordering is idempotent, and so they never matter in the formula. But they do, but different primes sampled define different probability distributions. So we might want to sample different kinds of primes. So here, for instance, we have our expansion as before, but we could also have the expansion where we marginalize B, and then we have C and not C, and then we have these primes which are in fact mutually exclusive and exhaustive and obey the V tree, but they marginalize B. So after this, we have the elements here, and they're sampled according to our procedure here. And when we have subs which are a bottom constant, then we can remove them because they're always going to have the probability equals 0. Another thing that we can do after we have sampled the primes is compression. So compression basically takes two elements with same sub and replaces them with a single element where the sub remains the same, and the prime is a disjunction over the primes, the original primes. And compression is interesting because we are able to generate different distributions while we maintain the consistency of the formula. And so we can sample different probability distributions by generating different compressed circuits. And so, for instance, here we have the first and second element have same sub, and thus we can compress them into one. If we have n compressible elements, then we can generate a very big number of circuits. In particular, these correspond to the summation of every possible combination of element. And so this is a big sample size where we can compress, but for our work, we only explored a small subset of these compressions because we only compress once and move on. And if we want to compress, and if we want to uniformly sample a compressed circuit from these compressible elements, then we can figure out that the space of the distribution of circuits, of compressible circuits, correspond to the Pascal triangle's kth row, since it's basically a problem of combinatorics. And so if we have n compressible elements, and we compress n elements, for instance, we get a disjunction over this big disjunction here. But that's a problem because how do we efficiently compute a potentially complex disjunction? We do this by using binary decision diagrams, BDDs. BDDs are our way to efficiently represent logic formula and apply operations on them in polynomial time. So for instance, we have the operation reduce here, where we take a logic formula, a BDD, and we reduce it to an unreducible form, the canonical form of the formula in n log n time. We can also apply some operations, such as a disjunction or a conjunction onto BDDs, to formula, in also polynomial time. We can also restrict a formula given some instantiation in n log n, and also forget a variable. Here we have a formula phi on A, B, and C, and on the left-hand side we have the BDD, which represents this formula. So I'm going to show some results that we have so far. We have, here's a table on the likelihood of various synthetic data sets. These are synthetic data sets produced by sampling a random PSDD, applying random weights to their circuits, and then sampling 100 instances of a data set. These data sets have each different number of variables, increasing from 10 to 100. And on the table below here, we have the logic formula which are used for generating these data sets. So we have here a special case for data set 7, in which we gave the tautology. So basically there is no prior knowledge, there are no logical constraints for the data sets. It's a purely probabilistic setting. And so we sampled 10 PSDDs from our algorithm to compare against other probabilistic circuits. And so we took the worst case circuit, the best case circuit, and the average of all 10 circuits. We compared them to learn SPN in two settings, where one was an optimistic hyperparameter optimization of some product network, which are probabilistic circuits similar to PSDDs, but they do not have the same restrictions that PSDDs have. So they are more flexible, but they are not able to encode logic formula. And so this LSPN optimistic competitor here had their hyperparameters optimized on the test set. And so it gives very, very optimistic results. LSPN CV is the learn SPN algorithm in a cross-validation setting, in which we took the training set and split it into validation and training, and then optimize the hyperparameters only on the training set, so it's a more realistic setting. And CLT is the Strudel-Chaulio tree algorithm that I mentioned in the related work section. And CNET is a cut set network algorithm, which is cut set networks are probabilistic circuits similar to probabilistic sentential decision diagrams. And so we can see here that the best sampled circuit consistently competes with LearnSP and Optimistic, and we can see here that it is often first place, and when it's not first place, it's second place. And even the average is second place sometimes, and we can see that even the average is very competitive against other probabilistic circuit learning algorithms. That's it. Thank you.